Hello, in this video we'll be looking at collisions, that's elastic and inelastic collisions, and looking at the conservation of energy, and in particular the conservation of kinetic energy. Now, energy of course in collisions is always conserved, but kinetic energy is not. If two bodies collide and kinetic energy is conserved, that is an elastic collision. If two bodies collide and kinetic energy is not conserved, that is an inelastic collision. Now just remind you of the equation: kinetic energy is equal to half mv squared. Now, most collisions in real life, most collisions with real size objects, as such, macro size objects if you like, are inelastic. Cars, trains, balls, footballs, cricket, balls and bats. Inelastic collisions, kinetic energy is not conserved, and the kinetic energy of the objects that collide are converted mostly to heat and sound. In fact, all energy is effectively eventually converted into heat. Now, elastic collisions in reality only occur between atoms and molecules, when the only possible way for energy to express itself is as kinetic energy, because that is the velocity of the particles, velocity of the molecules and atoms, and that is the definition of what gives rise to temperature. Temperature being the average kinetic energy of a system. Okay, now let's look at two examples. First of all, we'll look at an inelastic collision, and we'll calculate the kinetic energy lost, and then we'll look at an elastic collision. So, okay, first of all, let's go for an inelastic collision. So we have here two trolleys that are dead set to collide with each other. Okay, this is before the collision. This one is 2 kilograms of mass with a velocity of 5 meters per second, and this one has 3 kilograms of mass with a velocity of 2 meters per second. Now, after the collision, now I've done the calculations on this already. After the collision, what's happening is they join together, and they've got a combined mass of 5 kilograms moved with a velocity of 1.8 meters per second. Okay, so this is before collision, this is after. So let's have a look. So the kinetic energy before, using half mv squared, is a half times 2 times 5 squared for that body there, plus a half times 2 times now. In fact, because that 2 meters per second is going that way, we could write that as minus 2 squared. Not that it makes any difference, because that becomes positive. So that gives the total kinetic energy of, well, that comes out to 25, and this comes out as, oh, that's a 3, isn't it? Got a mass of 3 there. It comes out as 9. 6, so therefore gives a total of 31 joules. Okay, that's the kinetic energy before the collision, 31 joules. Let's have a look at what's going on after and compare. So I'm going to rub up the top here to give some space. So afterwards, using exactly the same, so kinetic energy after the collision is equal to half times 5 times 0.8 squared. Okay, and that comes out as, so let's check on the calculator. Okay, 1.6 joules. So clearly, huge amount of kinetic energy has been converted into other forms of energy, and the loss in kinetic energy is equal to 29.4 joules. So clearly an inelastic collision. Now we'll have a look at an elastic collision between an atom and a molecule. So what we're going to have is we're going to have a proton of mass m moving to velocity of 10u, colliding with a stationary helium molecule with a mass of 4m, 4 times the mass of a proton approximately, with no velocity at all. So that's before. And after the collision, the proton moves off backwards at that's minus 6u. I'm going to point in that direction. I'm sort of breaking vector rules really as such, so I should be pointing in that direction, putting minus 6u, but you can get the idea. And we'll have it, and it goes the helium, so this is still mass m, and the 4m helium moves in the positive direction at a velocity of 4u. So there you go. So now here, what we're going to do now, let's look at the kinetic energy before and after. So the kinetic energy in the before situation, so it's just the kinetic energy of this particle here, is equal to a half m times 10u all squared, which equals 50 mu squared. That's kinetic energy before. There we go, I'll do it in. That's for the before situation. And the after situation, so after situation, the kinetic energy is, well, those two particles both have kinetic energy. So that's a half times m times minus 6u all squared, plus the kinetic energy of this, which is a half times 4m times 4u all squared. Okay, and that will lead us to 18 mu squared for this, plus that will come out as 32 mu squared, which gives a total of after the kinetic energy equals 50 mu squared, and the before situation was also 50 mu squared, so therefore this is a perfectly elastic collision. Kinetic energy was conserved.